The Deutsch-Jozsa algorithm is a quantum algorithm expressed by this function. The problem involves determining if the given Boolean function is constant or balanced. Constant indicates that the output is all zeros or all ones, or balanced is that the output is made up of half zeros and half ones, or in the case if it's not constant, it's balanced. So let's look into the classical approach. Beginning with the first input, x of 1, we evaluate f of x of 1, which will output a 0 or a 1. Next, we have the second input, and now we evaluate f of x of 2, and the output will also be a 0 or a 1. If the output of f of x1 is going to be equal to the output of f of x2, then we can conclude that the function's constant. But if the output of f of x1 is not equal to the output of f of x2, then we can conclude it's balanced, indicating a mix of zeros and ones. The best case scenario of this problem involves two evaluations, which is evaluating f of x1 and f of x2, and then we're going to compare the output. Now let's look into an example of the best case scenario. So reiterating, we're going to determine if the function is constant or balanced. So the first case is constant example. We have the two evaluations, and then we're going to compare their outputs. We see that they're equal, so the function is constant. Case 2 is a balanced example, so we do two evaluations and then compare their outputs. We see that they're not equal, so we know that the function is balanced. In conclusion, the best case scenario is only two evaluations. Now let's look into the average case scenario. We have 2 to the n-1 plus 1 over 2 evaluations, which includes multiple inputs, and evaluating approximately half of the outputs and determining if the function is balanced or constant. Now let's look into an example of the average case scenario, which is evaluating the outputs until there's a difference. So looking at these outputs, we get to the last one, and we see that the output is 1. So this indicates a balanced function. The worst case scenario is similar to the average case, but there's only 2 to the n-1 plus 1 evaluations. And this is where you have to test all of the inputs and compare each of them to confirm if the function output is going to be constant or balanced. Finally, we're looking at the quantum approach of this problem, which demonstrates the power of quantum parallelism utilizing quantum gates and superposition. Most importantly, there's only one evaluation for every scenario. Now let's look into the steps of this algorithm. We're going to start with initialization. So first, you need to prepare n qubits in the form of ket 0, XOR 1. And also, you need to prepare a qubit in the form of ket 1. Using these qubits, we're going to apply the Hadamard gates to each of them. This creates a superposition state for all of the qubits. Here, the Hadamard gate is applied to ket 0 and to ket 1. The next step is applying the oracle. The oracle represents a function in a quantum computer and performs a transformation to modify the quantum state. We have ket x as the input register and ket y as the oracle qubit. We can see the oracle represented by this equation. The oracle applies f of x to all of the values simultaneously, which is where the one evaluation comes into play. So, after the oracle is applied, a final Hadamard gate is applied. This operation interferes with the quantum amplitudes or different states, amplifying certain measurement outcomes while canceling others. This allows us to perform the final state measurement. So we're measuring the first n qubits, and if the result outputs ket 0 XOR n, then we can conclude that the function is constant. Any other result indicates that it is a balanced function. So, in conclusion, the quantum approach is much faster, which demonstrates the power of quantum parallelism.